Okay, good afternoon, colleagues, ladies and gentlemen. Welcome to the President's HKIAS Distinguished Lecture Series. Today's speaker is the President himself. Okay, so what I do is I'll give a very, very short introduction, and then we will go straight into the lecture. Something about the speaker today. Professor Way Kuo is a member of U.S. National Academy of Engineering, Academia Sinica in Taiwan, and Hong Kong Academy of Sciences. He is renowned for his work in design for reliability, including electronics and energy systems. He was on the senior management team of Oak Ridge National Laboratory and served as Dean of Engineering at the University of Tennessee before appointed President of City University of Hong Kong in 2008. Professor Kuo was the first invited foreign expert to conduct post-accident assessment on the Fukushima power plant after the 2011 earthquakes. He has co-authored 7 academic books. In addition, his very popular science book, Critical Reflections on Nuclear and Renewable Energy, widely 2013, was translated to Japanese, French, and Russian, and published, of course, in Tokyo, Paris, and Moscow. He has been invited to deliver dozens of speeches on this particular topic across the world. He has served for 16 years as the editor-in-chief of IEEE Transaction on Reliability. If I were to give a full introduction, it would take hours, so I better stop here. And I'd like to invite our speaker today, Professor Way Kuo, to give the lecture. I'll come back in the question time. So over to you, President.
Thank you. Thank you, Paul. I'm going to discuss the data-driven management, of course, with emphasis on the COVID-19 and some related issue on nuclear power plant accident. I should say good afternoon and good morning in Europe, some of the friends there, and good midnight on the East Coast, New York time, Ohio, and I don't know, good sleep in California at 12 o'clock, at that time. So this is an important subject. Everybody has shown a lot of interest in this one. I think I can use this microphone without this one, right? Okay. In January 2020, this year, 9 months ago, we noticed a report of COVID-19. And we start to watch in here the very unusual development of seemingly high death rate of patients who caught a special virus. And we started to put eyes on the development. On January 20th, a case was identified in the west coast of the United States. On the 23rd of January, the first case was reported in Hong Kong. So in the morning of 24th, we take a look at the map, and we find out this is spread many places. In addition to the mainland China, Hong Kong, there are about 130-some cases else place in the whole world. It's just like Brownian motion in the stochastic process. It spread very fast in the beginning. And then we decided in the cabinet, many people would know, on the 24th, the cabinet meeting of City University Hong Kong, we said, we need to be serious about this to start some distance, lecturing. So we decided on February 1st to 6th, all faculty and teaching staffs, including myself as the president, should take special training in offering distance courses through distance learning and we label it as CTU learning. On February 7th, officially, CTU launched CTU learning. This is the first in the whole world offering all courses, real-time, on schedule, campus-wise, to both graduate and undergraduate courses. Of course, at that time, a few people think we have overdone it, but very quickly, people also noticed that CTU has made the right decision. The decision was made based on the data we've seen. It's not an imagination, it's not just a guess. Nothing happened by coincidence. Now we are entering the chapter 2 of CTU learning, and we are making even a little bit more modification, such as the hybrid learning mode through the office of the provost and many staff at CTU. So here's what happened. And as I mentioned, everything based on data. So we pull out the WHO data, and we do some curve fitting. In this chart, there are two sets of data. The gray one is the number of cases identified of COVID-19. And the red is the cumulative death reported by WHO. Since December 2019, the COVID-19 has triggered a global health, economical, and social crisis of staggering proportions. The virus continues to proliferate as of today. You look at this data, we did some curve fitting. The cumulative cases, the best fit from January 1st would be to use quadratic fitting. And the accumulated death, there seem to have 3 sections. I tell you, this is very tricky, this one. Once I show you the next curve, you will be amazed. And the first one seemed to be linear, and the second one is also linear. After April, it's really linear fitting. So what I did was, we start from April, we find out the cumulative cases. Actually, it's exponential curve. The cumulative death is very linear, and surprisingly, the R square is either 0.9 or 0.8. Just quite amazing. And notice that as of today, there is no vaccine available. The case fatality rate drops very sharply. If you take the red line divided by the gray curve, you will see the cases grow exponentially, the death is so linear, and that means the case fatality rate actually drops, okay, quite sharply. In the whole world, this is based on the global data. We're not looking at individual ones. And there's no treatment, no vaccine treatment at this moment, as you know. And the society, the whole world is really uneasy. There are demonstrations many places, and certainly some communities are handling the crisis better than the others. So in this talk, I will not address individual communities' attitude or success. I look at the global thing, and as I mentioned, it's really a very typical Brownian motion. Finally, something like this is not the first time occurring in human history. There are many cases. As you know, in the 1347 to 1352, the famous Black Death killed, according to record, tens of millions of people. So this is nothing new. But in recent history, within last 100 years, this is certainly very scary. And this is something we have to handle. I took the number of cumulative deaths divided by the number of cases. And to build up this function, this is the case fatality rate of COVID-19. And this curve, there occur three sets of curves here. The first one is the gray one. The gray curve is exactly the point when the people who have died divide by how many cases. Because the increasing function of the cases, this must be the lower bound of the case fatality rate. Given that I have no real data, so at least I know this gray one must be lower bound. According to lower bound, somewhere in April, the case fatality rate is 10%. The death rate is 10%. And the second one is the blue one. The blue one assumes there's a delay of 2 weeks after the person had been identified to have caught COVID-19. And finally, the red one is a simulated curve based on the real number of deaths and the real number of accumulated cases. So the red one is a likely one, which assumes the following. Assume those who die, 50% will be, say, wait for 2 weeks after they caught the virus. And 30%, they say 1 month after they caught the virus. And finally, 20% will be 3 months. So we simulate it randomly to get this red one. And this curve, all these three curves are actually quite very interesting. You look at the first part from January to April, it's very noisy. It's very funny. That's very abnormal. It confirms that. The first part shows before April, the reporting must be very messy, not dependable. Something wrong with reporting. The noises are stronger than signals. You cannot use the data there. This is what I call infant mortality of a system. That means in the beginning, it's unstable. The reporting lines, you got it. You cannot use it. It's not until April the worldwide data shows some dependable trend. And you look at the first set of ABC, those are based on the real data. Then the bottom set, because the previous curve I have shown you, the really good fitting. So if everything moves very nicely, you will find that somewhere between March, before March 30th and June 19th, the case fatality rate will be reach 0.1% this year. In other words, in like 5 months from today, the case fatality will drop to 10%. And then between July 31st and October 19th, the fatality rate will drop to 0.01%. And then further, if you wait until November 28th, 2020, and February 15th, 2022, the mortality rate will drop to 0.001%, assuming that no vaccination and everything goes smoothly as we do today. There's no extra effort other than what we are doing today. Of course, that's assumption. Once you reach 0.001%, it becomes annual seasonal influenza, okay? So somewhere between here and here, between July next year till perhaps the end of next year, you should reach a steady state. If improved medical assistance is available through vaccination or something else, then the dates will be moved earlier. Okay. We mentioned case fertility rates. Let's make some case fertility rates analysis. In this particular figure, there are two sets of colors there. The green ones shows you the number of deaths either annually or at one time. And the red color shows the case fertility rate. As of today, literally, we know 30 million people suffer from COVID-19 and more than 1 million people die of it. The case fertility rate as of today is roughly 3%. So case fertility rate today, as of today, is 3%. It was 10% about 4 months ago. You look at the green part, the annual traffic accidents on the whole world, it killed about 1.35 million people. Are you amazed? And each year, there are 800,000 people kill themselves. And for your information, all of the 800,000, there are more men than women, which means perhaps men are weaker than women. So some of the women here be nice to men. And the case fertility rate, it goes from SARS and the Merck and the COVID-19. It shows you a lot of variations. At the end, we share with you the nuclear accidents, such as Fukushima nuclear accidents as of today. It kills at the most, one person only. Even that person was debatable, okay? But you look at the curve, the worst case is environmental pollution as of today. The environmental pollutions are most significant. Each year, according to WHO, it kills 6.5 million people. Lung cancers and other pollution-related disease are the #1 cause of death in many places. It jumped from lower ranking to the #1 because of the pollution. Furthermore, in addition to that, at least 20% of the population, they are suffering without electricity, without clean water, no schooling, without cooked food, and without reasonable medical care, and they have had short lifespan. They live in the less developed countries and areas, and yet receive very little attention from us. Speaking of those people who are lower end in terms of income, I also noticed that one data point from France government, I believe this is true in every places. COVID-19 is without exception that the people suffer more. According to the French government, the low-income people have 8 times of the chance to suffer from COVID-19 pandemic than the others. And you can tell the poor people seem to suffer more. So this COVID-19 is reasonable to assume that the poor people will suffer more in terms of both catching the pandemic and will die out of it. Okay. We look at some economical aspect. In this curve, I plot the impact on GDP percentage per death versus number of deaths. From this curve, the Fukushima nuclear accidents has the greatest impact in terms of per person GDP. On the other hand, air pollution has killed more people, but has less impact economically. If you don't want to look at this curve, let's look at if we consider the expected loss of lives calculated by multiplying the probability of occurrence of accidents by the number of casualties. It will show that operating nuclear power plants incurs the minimum expected loss. It's the safest one. On the other hand, if the expected loss is calculated based on how people perceive the world through the street politics and the perception in recent human history, operating nuclear power plant, when an accident occurred, would attract the highest attention, with the next one being COVID-19. So it depends on how you look at the expected loss. We can conclude that the disproportionately huge number of casualties per annum due to pollution, traffic accident, and suicide seem to have induced far less impact in nuclear power plant. For that reason, we are forced to pay close attention to pandemic outbreaks and the nuclear accidents. So depending on how you look at the expected loss, if you purely based on casualty, then it may not be the most serious one. But if you look at the perception and the effect of human uneasiness, then nuclear power plant operation, particularly after the accident occurred and the pandemic accident as we are facing today, are the one most serious and need to be looked into very carefully. If we look at another aspect of economic loss, our common belief is that if we have a tight control in the society, such as people don't go out and cannot travel, everything, the common belief of that one is it can stop you from being caught by COVID-19. Therefore, the death rate will drop, but it will cause serious economical downturn decline. That's just common feeling about it. According to a report by Oxford, which is this curve, this figure, such a common belief is not true. If you take a few exceptions out of here, like a corner, say United States, Netherlands, and this part of the Philippines and Tunisia, you look at the others, it shows the other way around. Namely, if you have a tight control, it gives you low death rate, but also reduce your economic decline. Although it's not conclusive, but it is certainly not conclusive to say the control will hurt your economic growth. It is just not conclusive one way or the other. There must be something else in the whole thing. So even look at economical aspect, there are many ways to look at the issue. So Taiwan and UK are good example to show on the chart. They are on the lines. If you take those exceptions out of the picture. So what is going on? This is the key topic I want to share with people. The key issue is whether we look at nuclear power plant or look at pandemic or other major crises. We need to have a command, control, communication, information. So be high level of control. There are 4 messages delivered in this particular chart. And from this chart, we can review the shortfalls of nuclear power plant accident, dealing with it, and the shortfall of dealing with the pandemic COVID-19 globally. I'm not talking about specific countries or specific areas. First one, we need to shorten and simplify the transmission of signal from the original data to C3I. Data is important. We need to create a direct pathway for the original data to reach the commander or C3I to minimize the delays. Simultaneous data transmission through the middle levels is useful for early preparation for possible actions. There are 2 kinds of data transmission. One is reported data, and the other one is for the decision makers to make a decision based on the data they have. And we have a shortfall in both cases. I can be specific. The reason Fukushima nuclear power accident was so terribly hurting the community is because the reporting of data has been slowed, even cut short. The handling of the Fukushima nuclear accidents really hurts the decision making. And once the decision has been made and the decision makers also stall to make a decision, at that time, it's economical concern. The reason was a nuclear power plant is very expensive, and the shutdown, that means you shut down everything. Therefore, they are hoping there are some ways or will make it works, although it did not work. Likewise, for COVID-19, I don't have to tell you specifically. There are several countries and places. The information transmitted from the grassroots to the decision maker has been either delayed or ignorant, and decision makers either not making decision or making wrong decision. So the delays make this Brownian motion move very fast to every place. That's the facts, okay? So the information transmitting from the ground to the decision makers, if this moves well, we can cut down short the bureaucrats and chief commander of C3I. So that's one thing in common between the COVID-19 handling and Fukushima nuclear accidents. The second one is, at the outset of the crisis, when you reach the C3I center, we need to simulate outcomes of possible scenarios, and that has not been done nicely for both Fukushima nuclear accident as well as the COVID-19 in the early part. Until this moment, people start looking at this more carefully. The purpose is to minimize the collateral problems such as counterproductive, chaotic behavior caused by panic among the public can be minimized. This should be handled. It is not just a damage to the health economical. It also causes social unrest and a lot of societal problems. Without saying too much, the decisive decision made by Singapore government is a good one, I like to say, they make a decision quickly and they start to act quickly. The preparation for planning had to include special tangible elements. The special tangible elements include, in terms of COVID-19, such as the spare parts, such as the equipment. In terms of nuclear power plant, you need to have rescue teams. You have to be having some shelters for people to stay, and so on and so forth. So this is the second one. The third one is about every time in nuclear accidents. Whenever we start the nuclear power plant in 1954, and after each nuclear accident, a great deal of effort has been placed for safety. So we learn things when something happens. So crisis become an opportunity. So we handle in a snapshot cases. So whenever the crisis, we handle it. But what's still better needed is, and people don't pay attention to, what is the critical element of the system in operating a system that will cause a failure. So what is critical elements? The three nuclear power accidents in 1979, Three Mile Islands, 1986, this Russian, and then 2011, Fukushima nuclear power accidents. They all occurred with something in common, namely the human errors. And with a different system, the Russians have an outdated system with no concrete protection, and the Japanese system has the human error because they are operator of nuclear power plant and the government control. They all belong to the same family, and that family cover each other. And decision has been stopped. Right decision has been stopped, so it doesn't work well. So, in terms of COVID-19, it's very painful to see that the high number of infections among medical professionals. Do you know the medical professionals account for 4 to 25% of confirmed cases in different countries and areas? Not to mention the cross-infection between patients in hospital during COVID-19, which was also seen during SARS. People in Hong Kong can remember the SARS, during the SARS in Hong Kong, 21% of total infections worldwide are among hospital workers. That's very high, actually. I don't want to get into too deep about those infections. The cross-infection in the hospital between the patients and doctors and nurses and between patients themselves and so on. That's really very bad. In this case, there are solutions to handle. The solution in reliability is systematically handled. We use a four-tree analysis. The four-tree analysis is undertaken from top down. You look at what's the most critical elements. Deductive failure analysis, where undesired state of a system are eliminated step by step using Boolean logic. Number 4, the command control communication is a database. Do you know that in nuclear power plant, there are more non-nuclear engineers than nuclear engineers? I'm talking about professional ones. There are actually not that many nuclear engineers in nuclear power plant. Do you know why? Because when we look at nuclear power plant, we think it's a nuclear problem. No, it's not just nuclear problem. There are other problems. And some of them are even more critical than nuclear problems. Okay? Number 2, there are too many voices and opinion in the society. Everyone wants to speak out, and this is actually strongly discouraged. Finally, simulation should show that sometimes no action is better than with some actions. Not always you need to take action, okay? But how do you do to say that? Maybe so far I have shown you something a little bit abstract, but I want to give you an example and to see all of you have IQ, very high IQ. I just listened to a debate today, with U.S. president debate, and one says he's smarter than the other one. I'm sure you are smarter than. Okay, this is the bridge network, very famous in electrical circuit. The bridge network can be considered many ways. You can send the traffic here and get out of there, or you can send the water pump here and get some water out there, or you can send the signal here, get there. So this one has a bridge, has 5 elements. My question is, which one is the most critical element? Which one is the most critical element? Anyone want to give an answer? I asked a question to a basketball team's coach, this smart coach. I said, it so happened to have a 5-person play basketball. Where do you put the most important person in the team? Okay? And his answer was very intelligent. He said, depends on whom I play with. Okay? And also, what if all 5 persons are equally good? How do I put them there? Where do I put the weak one in some part? If they are all equally important, then number 3 certainly is important. But if they are not of the same reliability, same level of competence, it depends on the participation of the individual elements. The answer is not absolute. It depends many variations, depending on the system. And so the critical element, the whole thing in fault tree analysis should be able to tell you which one is important. I will tell you one example. There are many nuclear engineers, nuclear engineering experts here. The example is as follows. The nuclear power plant has been operated for more than half a century, and people think they know nuclear power plant very well, until when we had Fukushima nuclear power accident. We find out it is well known that the reactor need to water cool it. So water cooling system is very important. But people also know that if the water cooling, the system is broken, you should have spared pump to pump water to help you. People also know that. But people did not know was, in order to pump the water from the pump to the reactor, you need some electricity to pump it. It doesn't come out naturally. And so it happens. When this happens, they start the pump and, well, auto battery. So the reactor become melt down. That was why the accident happened. That's number one. This has never been addressed in any nuclear manual or anything because they think it's not important. The second thing is when the water are overheated, hydrogen has been generated. When there's a high concentration of hydrogen in a room, it's very dangerous. And the nuclear power plant, the system is a closed system. So there's a hydrogen explosion. Well, they did not identify the critical element of the system. They made everything perfect except that small part has a little probability. It happened and it killed everyone. So this is a famous example. The other example was what I just showed you. During SARS and this time, the cross-infection among hospital workers very high. When we are patient, we need hospital professionals to help us, either doctors or workers. But what if they got cross-infected among themselves? What if the ventilation system is not as good as enough? When the doctor and nurses and the other workers are sick, it hurts you and me. So the bottleneck, at least one bottleneck, is the hospital, right? So such a design concept should be applied to the One Health, what we call human, animals, and the environment system, or other living environment beyond hospital. We need to reduce the pandemic outbreaks and degree of panic in the community without saying too much. Identify critical elements. Identify the critical element that impact the spread of infectious disease is just as important as identifying the critical element in the fourth tree of operating nuclear power plant. Such an adoption could greatly reduce infection rate in highly susceptible communities. The HKIAS systems require input from, this is the conclusion, engineers and experts in infectious disease, bioinformatics, behavioral science, quality assurance, in addition to public health. The time I was preparing this slide, I got a letter from US academies. I read what US academies, the first sentence, it says, according to US national academies, science, engineering, and medicine are the heart of finding solutions to the crisis of pandemic. Isn't that interesting? So it is substantial, the point I'm making that the pandemic problem is a typical system problem. It involves a lot of elements. You need data to support to solve this. It's just like a nuclear problem. It's not just nuclear engineering problem. It's a nuclear engineering problem with a lot of other people to help them to get this. And this is what we call HKIAS, command, control, and communication. The talk is based on, partially, on the book, Importance Measure in Reliable Risk and Optimization. And this is a theoretical book. And the other article, Professor He Jifang and I just prepared, the crisis management, it will appear on the IEEE transaction reliability. It's coming in a few days. It's forthcoming. Both nuclear accident, outbreak, infectious disease are global issue to be handled by global HKIAS. Nuclear power plants and the COVID-19 have four things in common. I conclude with you. Number one, communication and the reporting system both have been very bad. Bad, I mean delay, ignorance, decision-making, tardy, and they both are the same, okay? So number one, they are both in common. They both have human errors as one critical element on the system, on the human errors. They both happen to have super high expected loss to the society. They are system problems, as I mentioned. Decisive or coordinated actions should be taken as data suggests. Let me say one more time. Sometimes no decision is a good decision, but no decision should be made after you make a simulation. You have to simulate all the situations. You need a data analysis to simulate the possible outcomes, consequences with expertise from different areas to draw a conclusion. Lesson taken from minimize the risk of operating nuclear power plant should be applied to that of minimizing the outbreaks of infectious disease such as COVID-19. What's needed in managing crisis through HKIAS that makes rapid and accurate decision based on data collected, no more and no less. Misuse of data is a real challenge that we see every day. Finally, I want to share with you, by looking at the charts, I hope you find out that for the same argument, we need to manage global environmental problems, such as air pollution, greenhouse gas emissions owing to excessive use of fossil fuels, water resources management, and the other critical elements that attracts less attention from us. So I was told I should limit my lecture to 50 minutes. It's 49 minutes now. So I conclude. I also want to know, also want to share with you, sorry that the data chart I have presented to you, I got tremendous help from Matthew and his team, Samantha. They have a massage of the data and look in this. So I'm very thankful. Otherwise, I wouldn't be able to plot those charts.
Okay. Oh, President, please stay there. I think they would not let you go without asking questions. So we have around 300 participants online, but we can start from here. Sir Collins, please.
President, you made a very optimistic prediction about declining case fatality rate for COVID. But that was based on this curious difference between the functions for the overall case numbers, exponential roughly, and the linear increase in deaths. Yeah. But to extrapolate that into the future implies that the cause of that difference is going to continue. I think it's unlikely. The cause, almost certainly the cause of the decreasing death rate in the last 2 or 3 months has been the recognition of better methods of treatment.
Sure.
Dexamethasone, exactly when oxygen therapy should be applied, and so on. So those are not continuing effects, they're transient effects. So I fear that the 1% or so overall death rate we have now is likely to be the minimum without the introduction of vaccines, of course.
Sure. First of all, I hope I did not use a prediction, because prediction is very dangerous. I didn't want to say that. I'm just saying the trend. Lucky enough, we have 10 months data to predict 4 months data. So it's just a foreseeable future if something may happen without the vaccination. And I don't want to make it conclusive. Yeah. Yes, Klaus?
So I was intrigued by the case fatality rate chart you showed. And what occurred to me was that, the calculations of case fatality rates for the different conditions must be different, right? Both on a time scale and also how you calculate them, how much you miss and so on. So you have any comments on that?
Oh, no, certainly. Can you be more specific about what?
Yeah, for example, I would say that, if you die directly from a car accident,
okay.
You died from a car accident, whereas you died from air pollution.
No, I understand. If you recall, I did not use, I don't think I used a car accident, I call it a case fatality rate. It's not right to do that.
Cumulative deaths.
Right. That's annual death of annual deaths. Yeah, the case fatality rate I only use the medical disease. Yeah, for the suicide and air pollution, those are annual death number. Yeah. They are not
but the basis of calculation must be different as compared to, for example.
Oh, definitely. Therefore, I don't call it a case fatality rate. I just say total number of deaths annually.
Even the total number of deaths must be different. Like, for example, influenza deaths are calculated by excess mortalities. So what I'm saying, I guess, is that the certainty that the death was caused by a car accident is much higher than to say this person died from COVID-19 or from influenza virus infection. You can be much more certain that the person died from suicide or a car accident, as opposed to this person died from an infectious disease, for example, unless it's very clear.
Actually, it's clear. Can I tell you a joke? I didn't tell you a joke. It happened in Old Region Nation.
Every talk must have a joke.
Yeah, and there was a statistician like to be very picking about analyzing data, and Paul is one of the renowned biologists. He would do this.
Joke, okay?
Right. And so there was one person who was driving and died of a car accident. And when the doctor come to examine him, one doctor says because he had a heart attack. And another doctor come in and say, well, he had a heart attack because he collided the car first. So you had to put the cause of that person's death. And so they are totally different things. So we did not put this as an analysis so detailed about that.
But before the next question, I'd just like to remind the participants online, you're most welcome to ask questions. So please type your question in. I'll make sure that the president will react to it, okay? So what's the next one? Joe, then David, okay? Professor Chin?
Yeah, thank you, Mr. President, for a very nice talk. I have many questions, but I would like just to ask one quick one, easy one. But I like the hard ones, actually, the curve fitting for the data analytics. That's what I like the most. But I'll ask this one since some of us listened to the presidential debate of the US. And it turns out masks or wearing masks is one of the major subject of debate between the two candidates. So the question is also related to, you read the first sentence of the letter from the academies. Don't we have enough evidence that we don't need to debate on whether one should wear masks? I hope that's clearer, therefore the world will get over with this pandemic faster. Thank you.
Okay. Well, Klaus, you can answer that question.
My assessment is that the evidence is very clear about wearing masks. I think the problem came really, it's a communication issue, because initially, because of the shortage of PPE, including masks, officials wanted to make sure that actually the healthcare workers, nurses, doctors that were most exposed got access to masks. So that meant sort of a very deliberate and somewhat wavering argument about the efficacy of masks. But since then, I think it's absolutely clear. I mean, Robert Redfield said, this is more effective than a vaccine, and I think I agree.
Okay.
David, there's one question that came in. Okay, you go first, and then I'll get the question online. You go first.
So I was going to ask, you mentioned, the way to one approach to dealing with this is a systems kind of question. You talked about, communication delays. You talked about doing simulations. You have all these different aspects in the system. So if you have a certain amount of money you want to invest in fixing the problem, how do you make the decision of whether you should decrease the communications delay or increasing the fidelity of the simulations? How do you make those kinds of decisions in a system sense?
You ask a tough question, and there's another question people ask very similar to this. Well, the key question is, should you look at the global government and control? You see, it's getting half philosophical, half political. The philosophical is I happened to listen to the debate of the presidential candidate of the USA, and you certainly need a good political leader to be able to delegate your things to the other people to do it. Okay, so I did not talk too much about CQI. The CQI essentially says you have to have one command center. The command center should have one focused person in charge. And that person, you need to get a conscientious decision to make a decision. And the so-called delayed communication means that you have to have the right data to make a decision. And you should have a team with expertise I mentioned to simulate the situation. So today, I think we agree we're doing better than, say, 5 months ago. And people converge a little bit. But there is also a delay of 5 months. And that's because there's no concerted effort. In this regard, a nuclear community is doing better than non-nuclear community. maybe because they are half a century history to deal with those cases. So everything happening in nuclear power plant, you will know that in Europe what happens is, and there's a group of people to digest and make a decision and to decide what to do. So I would say you need to have a good decision makers to look at this, and you need to embrace experts to get into the team. If something we don't know, just say we don't know, get other people to come in. If we do things right, I think it will not be too expensive. Of course, you can say it's easy to say it. It's important to pick up good political leaders or technical leaders to help the community.
Okay. I think, President, you answered the first question already in response to David. The second question is, you mentioned about deaths due to COVID. So this colleague is asking, how certain are we that when we say that what percentage people die out of COVID, there's uncertainty in that. So
sure.
How do we deal with that? If our data is not correct?
Okay, I have to say my data I rely on Matthew to give me right data, and Matthew rely on WHO. I don't want to make this really, I will write this up, but we have to do a little bit of study just to give you a concept. The data amazes me. It's 0.99 R square for the exponential test. I just don't, it's just quite amazing, you know. But anyway, it was real data from WHO. Yes, there are uncertainty. That's also part of Sir's question, whether this will sustain that way, okay? But it has sustained for 6-7 months already, maybe 8 months. I think it's going to be that way at least in the next 2-3 months.
Okay.
Of course, we are improving ourselves in terms of taking care of ourselves, and that will contribute to it. Again, I'm looking at a global. I'm not looking at individual countries, areas. There are a lot of variations. I don't want to mention to that. And some people are doing better. But there's a beauty look at global. In a larger sample theory, and this is a large number, so it certainly converge globally. I think it's a good proof for a large number theory. Sorry, Klaus.
I think, you know, my observation is kind of, and I would like if you could comment, but there's obviously a communication. So Donald Trump is not often right, but he is right in that if you test more, you will find more. So our increase in testing and the identification of more cases, and then obviously skews the relation between death and cases towards, you know,
sure,
lowering the case fatality rate. That is one thing, and the other thing that Colin said, that, you know, we're getting much better, at least in some parts of the world, in treating this disease. So that would probably contribute to the decline.
And let's just hope it will continue that way. In fact, there's no reason not to believe so for the time being.
Okay, any more questions?
Okay, here's another question.
Any questions? So, President, what should Hong Kong government do in regard to COVID-19,
Paul,
based on your data?
Actually, you're a very smart person. Paul has very high IQ. I should give you answer in my talk already. If I say too much, it will be redundant.
So everybody got the answer. Very good. Okay.
I delivered the answer in my talk. Because I'm the president for CTU, I have to stay politically neutral and not to mention the sense. And I mean it.
I just give time for them to ask questions.
Personality is the actually transaction with getting price management from nuclear acid to operate COVID-19. I found there's a similarity between the management of nuclear
Yes.
acid, because we have, as you said, we have many experiences, okay, about the crisis management, about emergency management, and think about the performance this time in Taiwan and also in Macau and also in Hong Kong. actually, relatively, we are doing better than other parts of the world. And I think that's because we have some experience gained from SARS. Okay, so everybody wear a mask, after the first incident of the COVID-19. So I think that maybe the reason why Taiwan, Hong Kong, and Macau are doing better. Mm-hmm. Yeah, because of the experience gained from the SARS.
Yes. One question here I can answer. The question says there's a variation about the case fatality rate. And then he says people may die of more issues, not just directly by COVID-19. That question has been given to us all the time. But given such a large sample, I think we can ignore that differences that much. For small sample problem, that is the issue. I gave you the example about car accident and heart attack. Because you have to identify, is that because heart attack that causes car accident or the other way around when you only have a few cases. But when you have such a large one, there is certainly someone maybe died of the others. That's what we need bioinformatics to help analyze the cause of the death. I think that would be not as significant. Yes?
Professor Chin?
Looks like we have time for one more. So I'll ask this curve fitting of exponential fitting that's fitted beautifully for 9 months or for the time you're fitting. That's very nice. I think from the data scientist point of view, the beauty of that exponential fitting is that it's parsimonious. You have only 2 parameters to fit the entire trend, very nicely. And the difference between that fitting from a polynomial is actually you can expand that polynomial with that exponential with the Taylor series.
Okay.
You get it into a third-order polynomial, you might find that's just like another polynomial fitting. However, your exponential model has only 2 parameters.
Yes.
And you can take a logarithm to make it linear. So it's going to be an intercept and that shoulder, that power, the power part. So it's a beautiful fitting, I would say, with the exponential. It fits all the principles in data science. Okay.
Thank you. I want also to substantiate one comment I made. In the beginning, there's a lot of communication delay, decision delay, and a lot of tardiness. It's just shown, look at this yellow box. I don't know why this is go to it. Look at this one. I mean, this is a perfect example to show that before April, the world is out of control. It can't be that way. There's no such a thing. That means nobody is in charge. Everybody put finger on the others. And this just shows you this. I have asked to check this again. It's just so funny. That means people really did not get serious until April. Say, okay, we got to be careful.
There's one question coming in.
Yes.
Do you think you need to screen the data before you do the fitting? Because not all the data are of the same quality. I think that's what the question is.
Well, that's a standard statistical analysis. You have to check on that, of course. And we assume WHO has done that.
You use WHO data?
Yeah, you have to, definitely. That's a part of analysis. Yeah. By the way, when I say data, I don't really mean numbers only, okay? Data can be parametric and non-parametric. Sometimes non-parametric is more important than parametric. But either way, you have to make a decision based on the data you have. I hate to say it, collectively, we developed the CTU learning. There are many people deserve the credit. Our provost, you, Jianlu, and Matthew, and Horace, and where's Richard?
And Alex.
And Helen. I mean, you recall we have a meeting, we look at, say, this look one, and then we say, we need to look at whether we should offer this. And that's why we're the first one. I mean, at that time, we don't have parametric data. We have the map. I show you. I said the map shows, we just say, oh, wow, something's coming like crazy. So we should be ready for that. And sometimes people laugh at us a little bit. They say, well, sure, and we'd rather be safe. After a few months, we find we are right, you know.
Any further questions? Well, the President said it's science, engineering, and medics that are the core. Richard, Professor Walker, you're from social sciences. Do you have anything to add to that? Are you leaving that to us, just?
It's the people that make it work and the understanding.
Sure.
It's similar to what the President said in terms of communication and capital systems.
Yes.
You can have a systems theory, and there's a lot of research in public policy on emergency preparedness and so forth. But the operations of the systems are essential. So with Hurricane Katrina in the US, the US emergency systems collapsed, but a lack of leadership and a lack of coordination. So with any of these systems that we're seeing in place, it's about, you sort of touched on it in terms of behavioural sciences, it's about people, it's about those institutions and ensuring those things can come together with the science and with the technology and to ensure that responses can be developed.
Yeah. Any other questions? If not, I will pass the time over to Professor Huang.
I have a quiz.
Quiz.
I have a quiz. I always have. I have always on my talk. We have a quiz. Whoever got right first will get this baby.
Explain what this is.
Okay. You know what this is?
No, it is not. That's the point. It's not right. It's not right through.
Well, the C cube I. What does the first C stand for? Command. Who say command? This for you. Will you catch this?
Oh.
Perfect. Thank you. He's in charge. This is command. Okay. Thank you.
I'm Jacob Huang, director of the IAS. So I represent the Hong Kong IAS to present a crystal stand to the president. Okay.
Thank you. Thank you.
Okay. Thank you.
谢谢。Okay. Thanks. Thank you. Thank you.